Consumer augmented reality is progressing quickly, with great 6-degree of freedom, portable, and self-sustained head-mounted displays like the HoloLens and Magic Leap finding their way into many types of applications, from video games to surgical training. We focus on laparoscopic surgical training, which requires excellent hand-eye coordination and accuracy. Surgical trainees typically practice these skills on either very expensive equipment like the Da Vinci robotic trainer, which costs over $1 million, or very cheap devices that are very limited in technical capability, but are very easy to replicate at home. We focus on the latter, because low-cost surgical training is becoming crucial to the modern world. For example, in the COVID-19 pandemic of 2020, medical practitioners were very high in demand, but quarantine made it difficult to train them sufficiently for practice. While work exists on using AR for surgical training, it is usually limited by a reliance on synchronized cameras like point grays, which are extremely expensive and do not work with the game engines required to build AR apps, or Raspberry Pi cams, which do not interface well with other operating systems and also have the game engine incompatibility problem. Standard computer vision methods also do not allow these cameras to be tracked in motion, which is an important requirement for replicating accurate robotic surgery. In this paper, we develop and prototype a system that attempts to mitigate all of these problems at once. It tries to avoid hardware synchronization by instead running each camera, which independently predicts the apparatus pose, on a separate thread and pooling together the results with another pooler thread that streams these results to the AR device. It then uses forward kinematics applied to a set of local poses to automatically calibrate any number of cameras, given the measurements of the static markers on the apparatus that are visible to each camera. We prototype the system and run it on both the HoloLens 1 and the Magic Leap 1. Our visualization is somewhat limited as both devices' front-facing cameras do not approximate the user's perspective well. So first, we show the approximate alignment with videos taken by placing a camera behind the headset's lens, where the user's eye would be. First, we show the view through the HoloLens. As you can see, both the Vive trackers and the pegboard apparatus are aligned quite well. We find that the error is typically less than 2 mm unless tracking is completely lost. In this second demo, we show that the donut itself is also aligned well. Next, we show the Magic Leap view. It is also pretty well aligned, although we found slightly more error with this device, likely because of the more extreme front-facing camera location used to orient the entire space. The Magic Leap also has a very large near-clip plane of 37 centimeters, meaning you must be that far from something to see it. This is too large for this small tracking task, but the overall system still works for this device and could potentially expand to larger tracking tasks more appropriate for the Magic Leap. Finally, we show an example of the peg transfer task itself. The donut that is being moved changes colors when a different camera can see it. Notice two limitations of the system. First, there is a bit of latency in the donut's movement. We find that the manipulator pivots stop you from moving fast enough for this to be a major problem, but it is still something worth analyzing for future work. Second, note that there are discontinuities when swapping between the movable camera view and the static views. We currently do not interpolate between the views, and there is some jittering in the Vive tracker motion, so both of these problems should be solved in the future. There is also some inaccuracy in the placement of the markers on the sides of the pegboard. In this video, we show the individual camera predictions, which are clearly well aligned. This means that the markers themselves were not measured accurately for the final placement of the local camera predictions. Note that this is recorded with the front-facing camera, which, as noted before, is not a good representation of what the user sees. So there is some slight misalignment, but the point of this video is to show the transfer of the donut between cameras. To summarize, we have built a low-cost tracking system that can track both VR devices and small objects in an AR headset, which has not been done before to our knowledge at this accuracy. We also allow for movable cameras such as the manipulator cams, as well as arbitrary placement of as many cameras as you wish, assuming the PC has enough threads for them. We hope that this work is the first step in complex low-cost serious AR applications. Thank you for watching.